we are going to discuss a few more things about electrospinning and the electrospinning setup. And then we will talk about specifically electrospinning of pan, because that is our important carbon precursor. Okay, so let's start with the some more parameters. You remember how your electrospinning setup looks like, right? And you remember that some of the things that we talked about, there are two electrodes. There's a certain distance between the two electrodes. This distance, in the case of the traditional electrospinning, which we call only electrospinning, the far field electrospinning, you will have 10 to 12. So I had written 5 to 20 centimeter in the previous slide. In principle, yes, you can go between 5 and 20, but 10 to 12 is like the most common or most commonly used distance between the two electrodes. Now, what is important here is that your setup can be both vertical or horizontal. So the one that I had shown you, I told you that, so you had this needle from this side, one electrode, here, and then the flow of fibers. And over here you had your screen or your collector. Okay, so basically the fibers were fabricated horizontally. They were collected horizontally. Now we can also, why can't we have a setup like this where you have your needle on top and you have your collector in the bottom? So the answer is yes, we do have indeed both kinds of setups, and both have their own advantages and disadvantages. Okay. So in the case of vertical electrospinning, what is your advantage? The fact that you will have less wastage of fibers. So whatever is coming out, you are able to collect all of those particles, all of those fibers. But there is also a disadvantage of the vertical setup. The disadvantage is that, you remember, so yeah, here again I have shown you in the schematic, when you have this horizontal electrospinning setup, in that case you're only collecting the good fibers, let's say the thin fibers. And if you have slightly thicker fibers, or sometimes you may even have droplets, you may, because polymers may not always be perfectly uniform, the polymer solution. So sometimes you have lumps of polymer, so you may end up getting droplets because of that. Those things will then fall on the way. They will not be collected because of the gravity, they will already fall. But in the case of vertical electrospinning, you will have all of these things collected on top of your substrate. So in general, what happens is when people are conducting research, or they are doing experiments with certain new polymers and so on, they will use horizontal electrospinning, because you don't know what are the optimum conditions, and when do you get droplets and when do you get good fibers. In the case of industrial processes or well-established processes, however, you will use the vertical electrospinning setup, because there what is more important is that you don't end up wasting too much material. Okay, so in any case, both of these setups are widely used. Now what you can also do is you can change the size or shape of your collector. So till now, whatever I have shown you in the name of collector, that has been in a plate, and this plate, you can also attach a silicon wafer on top of this plate. Basically, you have a conductive plate. But what you can also do is you can change the shape and size of this collector. How will that make a difference, and why should you do that? Drum collector. This is indeed a very common collector nowadays. If you buy an electrospinning setup, you can actually buy these drum and disc collectors along with it. So drum collectors are basically, they are rotating at, so they are cylinders of metal. So they're connected. They are your electrode number 2, and then they are rotating at reasonably high speeds. Let's say 2000 rotations per minute. So what happens now? Now you're like winding the fibers, and when you're winding it, especially when your drum is rotating with that speed, then you also end up aligning the fibers, which does not happen in the case of a simple plate collector. Now, if you want to also position your fibers in a very, let's say a very thin or very narrow space, then you can use this disc collector. So disc also rotates, but you see, it's more like a CD, a compact disc, and you're just collecting the fibers at its edge. So now you have this very thin rope-like structure. However, again, you know that these kind of things you will only do for research purposes or for small scale fabrication, not for industrial application. There you use the simplest geometries, because also your process is very much optimized. Okay, so you can also design. So there are many other types of collectors also. These are the ones that are rather commercially available. You also can design your own collectors. You have various types of stages nowadays. You can all you need to do is sort of play with the electric field. Wherever you have your conductive collector, then the fibers will go and attach there. They will get attracted to it. You can also have to begin with, you can have collectors as simple as an aluminum foil. So you will have, if you just want, a large fabric-like sheet, then you can just collect them also on any conductive foil. So all kinds of collectors will can be prepared. Okay. Now, I have also written here, and probably also I said it in the previous class, that you can make your own electrospinner. So I have nothing against the companies who are selling electrospinning setups, but at the same time, whatever you need for research purposes, a small scale device can indeed be prepared at the lab scale. What you need to do, you need a high voltage power supply, you need a good stage. Okay, you may or may not need a good stage. You can sometimes also just have two electrodes, one needle syringe, and then any conductive substrate connected to the power supply, and maybe you need a syringe pump. That's all you need. You can actually prepare your own electrospinning setup. However, please take care of all the safety precautions, because you're working at very high voltages, and you may get shocks. And I have myself learned it the hard way. So I would like to tell you that do make sure, I think what is a good idea, which I should have done also, is that you place your entire setup inside a good closed chamber. And these chambers can generally be prepared using PMMA sheets. PMMA is polymethyl methacrylate. You get these kind of thick plastic transparent sheets, and you can just do some laser cutting and make your own box. And make sure that the doors are closed when you are running the electro, because you see, you're working at pretty high voltages. And especially if you're working with conductive polymers, you may also have some sparks here and there, especially for when you're performing optimization of for a new polymer. In that case, there is a possibility of accidents, so take care of all the safety precautions. And in the commercial electrospinners, typically if you open the door, then the voltage supply will the power supply will turn off automatically. So these kind of precautions must be taken care of. Okay. What industrial spinners also have is a multi-nozzle system. Multi-nozzle means, so you can imagine that a nozzle is again your spinneret or your needle. So you have, if you want to perform, or if you want to make really large sheets of electrospun fibers, what you can have is, you can have 10 nozzles. And 10 syringes and 10 pumps connected to it. So this is what indeed happens in the case of large-scale industrial fiber, especially for carbon fiber fabrication, because you need to then prepare really large, massive laminates in many cases. Or you need to also braid the fibers. You need to then you need a lot of quantity of the fibers. So in that case, you have one single collector, but you have multiple nozzles. So this is also a variation of it. Okay, yeah, so we already talked about the electrical conductivity of the polymers. You also know that, if your fiber connects the two electrodes, you may have some sparks. Okay, so this is generally about the electrospinning setup, and now let us specifically talk about the electrospinning of pan. So on this slide, I have shown you a lot of chemical structures. These are actually several steps that take place, several stages of the carbonization of pan. But before the carbonization, we also perform one more step in the case of pan. This is known as the stabilization step, and this is what we are going to talk about. Now here you see, this is your starting material, pan. What is interesting about it? So if you remember, in some of the lectures, I said that if you have aromatic rings, if you have these 6-membered rings already in the polymer, then it is a good idea. Then it will yield good and graphitic carbon. But in the case of pan, you see, you don't have that cyclic structure. It is what is known as aliphatic polymer. Okay. However, when you do get good quality carbon out of it, and the reason for that, this is why I'm showing all these chemical reactions. The reason is that there is a certain cyclization takes place, where your nitrogen atom behaves more of a, as an intermediate structure, or even you can call it a catalyst. And then you have these cyclic structures forming at a certain time point, and then you get good carbon which has graphitic content. Okay, so now let's first think about what is pan when you want to start working with pan. Okay, it looks like a white powder. When you purchase it, the typical molecular weights that you buy is around 150,000, but you can also get higher molecular weight pan. Higher molecular weight will have a longer chain length. That would change the viscoelastic properties. So in case you need it, then you can buy that. Anyway, the typical parameters for the for the electrospinning of pan are mentioned here. You take this powder and you make a solution. And the solution is, most common solvent for dissolving pan is dimethylformamide or DMF. You may have to heat it up to 70 degrees for a while to get a good solution. So now you get this solution of pan, and then for electrospinning, the parameters that you would typically use is 10 to 12 kilovolt. That is your voltage. And you will also, this concentration of the polymer solution is generally, it varies between 5 and 15. But you may also, for carbon, again, for industrial purposes, typically it's 10 to 12% solution weight by volume in DMF. So these are some of the parameters that you will use for pan carbonization. Okay, as I mentioned, before the carbonization, you will heat it in air between 240 and 350 degrees centigrade. Why are you doing this? This is the step which is known as the stabilization step. And over here now, if you look at this diagram or these reactions, you will see that you lose some water and oxygen. All of this is, or there is dehydrogenation at various steps. This entire thing is actually happening during your stabilization. So you do need some oxygen here. This dehydrogenation is what takes place during its during the initial the stabilization step. Okay. After that, so here also till here you need oxygen. Once you get this kind of cyclic structure or longer sort of you can call it further polymerization. But then also you're changing the chemical structure a little bit, but you get these kind of large structures. Then you perform the carbonization under the inert atmosphere, and here you see at 500 degrees you have this kind of chemical reaction, 700, something like this, and then finally you get these large carbon structures where you have some nitrogen atoms until maybe even 900 degrees you will still have nitrogen atoms in it, and that is why in order to get rid of the nitrogen, all the nitrogen pan fibers for making the carbon fibers, you will heat them to a much higher temperature rather than 900, because you will still have some nitrogen there. Okay, now this entire strategy was suggested by Fitzer. This is a very common, this is still the most extensively studied paper in this regard. So this is a proposed mechanism of decarbonization of pan. And this is where you also see what happens during stabilization. Okay, what else happens during stabilization? This is what we are going to learn now. But before that, let me show you some pictures. So this is how your electrospun pan mat looks. I think I had also shown this picture earlier. If you stabilize it, it looks something like this. So it looks a little brown. So if your mat becomes brown, don't worry, you've not burnt it yet. So this is all right. This is how the stabilized mat looks. And then when you carbonize it under the inert atmosphere, in this particular case, this was carbonized at 900 degrees. So this is how now your mat, now it converts into this carbon fiber mat. Carbon fibers, you would say that this looks a stiffer structure. It's not as flexible as the pan fibers. Yes, in fact, it's not as flexible, but it is still flexible enough. So right now it looks a little bit stiff in this particular picture, because number one, because you're comparing it with the pan fibers. Number two, also there is no solvent. There is at least a little bit of shrinkage. So there is some, the structure is not as freely, it's not able to move as freely as before. But if you take one little part of this mat, then you will see this one here. Then you will see that it is indeed flexible enough, And it depends on how you fabricate your structures, how many layers do you want in your fibers. Then you can also control the flexibility of your overall structure. Okay. So I was talking about the stabilization step and what else happens there. So you know that now you have certain oxidation and dehydrogenation steps that are taking place, and there is also some water molecule there, some water molecules and oxygen being produced as well. This reaction of stabilization. So because of all of these, you have both of the certain reactions taking place and also certain byproducts are being formed. This is a diffusion controlled reaction. When it is diffusion controlled reaction, that means you need, if you increase the temperature, diffusion increases in general. So you basically need, if you keep on increasing the temperature during your stabilization, then you will have a faster and better stabilization, but you're limited by the stabilization temperature, because if you go above 350 degrees, then you may end up either burning your polymer, or you may end up melting it. You may end up also deforming your fiber structure. So you don't know, even 350 is pretty high. People even would keep it below 300 in general. So what is a good idea in order to avoid the damage to the fibers? What you could do is you could just heat it not at very high temperature. So it has to be above 240, but you can keep it, let's say, at 270 or 300. You can keep it for a longer, for an extended duration, rather than trying to do it quickly. So if you do it, basically if you do it slowly and for a long time, then you will get better stabilization of your carbon fibers, of your stabilized pan fibers. Okay. Now, these fibers, once you have these stabilized fibers, then you would convert them into carbon. And that is done at a minimum temperature of 900 degrees. Okay. At 900, still you do not have very, you have maybe 97% carbon content in your carbon fibers if you perform the elemental analysis. Okay. So what we also need to understand a little bit is this pyrolysis mechanism. So I told you, when we were talking about pyrolysis, I told you that typically up to 700 degrees you will have the pyrolysis taking place. And after that you will have carbon-carbon bond formation, and at some point you will, at 900 you will get a reasonably good carbon network. So you can work with that, but then you further increase the temperature, then you get more graphitic content and you get rid of all the impurities. If you want to get pure graphite, you will go all the way to 3000 degrees, and you have to have a graphitizing polymer. Not all polymers will give you graphite. Okay, so what happens in the case of pan, and can we actually do, what do we know about the pyrolysis of pan, given it's such a common polymer? And also things that we know about pan, can they also be applied to other polymers? Okay, so what we can do is you place these fibers inside the furnace, and as in these pictures you can see, you take them out at so this is after stabilization. However, then I heat treat it for up to 400 degrees, and then I take the sample out. Then I heat treat it at 500 degrees, I take the sample out, 600, and so on. Or even I can have, at every 50 degrees I can take the sample out. There will be some rearrangement of bonds and certain chemical reactions, certain annealing of byproducts during the cool down also. But ignoring that, if I just take these materials and try to understand their properties, their elemental purity, their electrical conductivity, their mechanical properties, then we can get some idea about what's happening during the pyrolysis. Okay, so these materials, I would call them pan carbon intermediate materials, because they are neither pan nor carbon. So they are definitely not carbon. Even if you say carbon with high impurities, even that is not correct. It's better to not call them carbon. Sometimes people use the term char for these kind of materials, but we don't want to give the impression that this is formed by coking or charring. So in order to avoid any confusion, we just call them intermediate materials. Okay. So it seems, I will show you one plot on the next slide. It seems that most of the properties undergo a very sudden change around 700 degrees for polyacrylonitrile. What does that mean? You will have a lower electrical resistivity. The pan is insulating. So the material remains pretty much insulating. Maybe the electrical conductivity increases a little bit as you increase the carbonization temperature or pyrolysis temperature. However, at 700 you will see a sudden jump in electrical conductivity. So the materials that are prepared at temperatures higher than 700, you can call them electrically conductive. Before that, you will still have them in the insulating material range. Similarly, for the mechanical properties, the material will be very soft, but then suddenly it becomes stiffer at 700. Of course, this stiffness and also the electrical conductivity is not very good, very high at 700. And in fact, if you keep on increasing the temperature, you will then get further, increase in crystallinity, and therefore the properties will also improve. But from this, you can understand that there is some big change is happening in the material at around 700. And what is this change? Most likely, this is where you are getting rid of all the non-carbon atoms. Because initially you lose some atoms, you lose some oxygen, you lose some nitrogen, you lose, but hydrogen leaves later around 600 degrees. But then hydrogen is also leaving, also the remaining nitrogen. In the case of PAN, most of the hetero atoms, now we get rid of them at around 700. I'm saying most of them, not all of them, but you basically have a sudden release of byproducts just before the 700 point, and also you now have sort of a skeleton, your carbon skeleton prepared, or carbon network you can call it. That is what you now have at 700 degrees. Now you're doing the further heat treatment just for getting higher crystallinity and higher purity. So as mentioned, this is one plot. You can see here, this is approximately 700. And these are the materials which are the intermediate PAN carbon materials, and these are electrical properties. So this is electrical resistance, and this is the pyrolysis temperature. You can also plot mechanical properties and other properties. What is interesting is also for other polymers, maybe the temperature is not exactly 700, maybe it's 650, in some cases 720, something like that. But for many polymers, this is pretty much what you get. This is between 600 and 700, you will have this sudden change in properties. So keeping in mind that also furnace is not, these experiments were performed in the lab furnaces where even the furnace displays 700, maybe it is 696, something like that. So minor error is possible, but this is just to give you an idea that this is number one, this is what happens for PAN, and number two, this is one method of understanding the mechanism of pyrolysis. Okay, in the case of carbonization of PAN, there are a few more important things, especially when we talk about the carbonization aspects. If the fibers are ultra thin means less than 20 nanometer thin. These kind of fibers, they are often, they can be carbonized at a lower temperature. This is not just the case with PAN, but any polymer. When you have very small structures, but this effect of structure is only visible or only at least dominant when you have structures that are smaller than 20 nanometers. So extremely small structures, if you carbonize them, they can have both byproducts and defects annealing out very easily. So because of their high surface area. But as I mentioned, it does not happen in micro scale. This is often the case only at the nano scale, and especially fibers that are smaller than 20 nanometer. So in this case, you may get higher graphitic content at 900 itself. Now, one more interesting question arises: is PAN graphitizing or non-graphitizing type of polymer? What kind of carbon does it give? You actually, for the industrial carbon fiber fabrication, if you want to get a higher graphitic content, or if you want to call them graphite fibers, then you will still use mesophase pitch and you will not use polyacrylonitrile. In general, polyacrylonitrile is a non-graphitizing type polymer. However, there have been certain publications where people used certain stress from the beginning, or certain additives in the material, or even very high temperature special treatments can yield graphite-like crystallites at the end. But that is only when you have specific specialized treatments. In general, PAN is a non-graphitizing polymer, but we do not say that this is the fibers that we have are glass-like carbon fibers or graphite carbon fibers or non-graphitizing for that matter, for a couple of reasons. Number one, in the case of fibers, as I said, that the defects can anneal out easily. relatively easy. So you cannot always say that you are going to never get graphite out of it. Although under normal circumstances that does not happen, because there will be some curved carbons that are formed. There may be some fullerene-like structures, although in the case of fibers, it is less likely, because they, again, because of, especially when you have fibers as thin as 20 nanometer, then it is possible that these defects will anneal out. However, there will be some curved carbon structures. So this is more of a non-graphitizing type carbon, and that is why you should not get graphite out of it. But we also don't know exactly what's the mechanism of carbonization. Do we call it coking, and do we call it charring? That is also, so mostly it is coking process. But you see, in the case of pan, you have this cyclization going on. This is more complex compared to most of the other methods. So you do not really you do not specify what kind of whether it is a coking mechanism or charring mechanism. You just call the fibers that come out of it as carbon fibers. One thing we do know is that we do get a high carbon content in your in the fibers that come out of it. Okay. So there are some other things about carbon fibers. What happens at low temperatures? So low temperatures in the industrial case, you will call low temperature. 900 is a low temperature for industrial processes. Okay, because in industrial scale we are anyway not making fibers smaller than 20 nanometer, or so we have large enough fibers, and that is why you do not get much graphitic content at 900, and you would typically go for higher temperatures. What you can do if you want to get some graphitic content, again, that would be mostly for research purposes rather than for industrial applications. What you can also do is you can have some additives. So you can have metal nanoparticles. You can also have certain carbon additives, like you can add carbon nanotubes in your polyacrylonitrile solution. In the case of polyacrylonitrile, it's relatively easy because you're preparing a solution from a powder. At that time, you can also have some additive. Of course, you will have to optimize the concentration so that the material does not lose its spinability, so to say. So you can add, in these pictures, you can see that we added some carbon nanotubes into pan and then spun fibers out of it and then carbonized this entire thing again. So this material actually becomes your sort of a carbon-carbon composite material. What is the advantage of this entire process? I don't know if it is clear in these pictures, but if you can see over here, the regions that are close to the nanotubes, they show more graphitization because of this templating effect. That is that you can do to improve the graphitization. So we also see them in the transmission electron microscope images, and we also can do electrical conductivity measurements. So you will typically, if you have higher graphitic content, you will have higher electrical conductivity. So depending upon your application, so for sensing applications or also for gaining more mechanical strength, you can test different properties. What do you want from your fibers? One way of increasing graphitic content is also this, addition of either graphitic carbon nanomaterials, or of course you can also have this catalytic graphitization where you can have metal nanoparticles, for example iron. In that case, you will need to get rid of this iron or whatever metal afterwards from your fibers. So you will have to perform certain leaching experiments, etc. But there are certain methods of improving the graphitization in pan fibers. Okay, however, as I have mentioned before, that for the industrial graphitic or graphite fiber fabrication, again, graphitic and graphite. Graphitic is the content of graphitic crystallites typically in a disordered carbon material. Then as long as you can detect that peak of the graphite in XRD or any other spectroscopic or diffraction analyses, then you can call it graphitic. However, graphitic does not mean that there is any given fraction of crystallites. So it can keep on increasing, and that is why you will say that the graphitic content keeps on increasing at higher temperatures. This is valid for all carbon materials, not just fibers. But non-graphitizing would mean that it will never convert into perfect graphite. So that is what we have with in the case of pan fibers. You have, this is non-graphitizing, but it does get higher and higher and higher graphitic content as you keep on increasing the pyrolysis or heat treatment temperature, or if you increase or add, for example, carbon nanotubes, or you induce stress, or with other methods. You can these are some of the articles, then you can read, you can find them on the internet. There are ways of getting a very high graphitic content in pan derived fibers. Okay, so there are, as I mentioned, now you can read more about it. This is an area where you have overwhelming amount of literature. You can find several books, even several research articles, several review articles on carbon fibers, electrospinning, and pan-derived carbon fibers specifically. So this is one paper which I this is a paper from where I took that mechanism image, and there are many other papers. So if you're interested, you can read more about it.